So continue the previous topic of potential, electrostatic potential. Okay. So previous class we discussed about how to calculate a potential from the field. Okay, from electric field actually. We derive an expression for that is potential equal to I to S, and that is a potential surface, high potential surface, lower potential surface, and electric field from plus to minus, high potential to low potential, and delta x be the difference of lengths. Okay, that is I and F. So here the important is that now check that if that's a equipotential surface, suppose that's another equipotential surface, okay, and that is another equipotential surface, okay. So that is a high potential, that is a low potential, and electric field from high potential to low potential, meaning plus to minus direction, electric field in that direction. In that direction. Okay, they are actually parallel. Drawing is not look like a parallel, but they are a parallel line. Okay, they are parallel line, and a test charge. Suppose that I call a positive test charge from high potential surface Q naught to move a low potential surface. Okay, and the distance between two plates is called D. Distance between two equipotential surface. Okay, and if you choose an any point on that surface, suppose that point like here, the test charge when Q naught move from this path. Actually we check the test charge is path independent or not. Okay, calculate potential is path independent or not. Check that. So here we see the very carefully the diagram A. The test charge move from state path. From here I to that point is F. Initial to final, that's the path. The test charge move that gray color path here. Okay, and that is the Q naught, and there is a gap is D, and the electric field in that direction E, and ds vector same direction, because ds is called a small differential surface, that direction is same, and electric field and ds direction both the same. So high potential, that is vi, that is a final vf. Low potential, so vi is greater than vf. So test charge move. Now notes that the uh, test charge move in a straight line and from point I to F, point I to F, okay, along the direction of a uniform external field, along the direction of uniform external electric field. So that's the uniform external electric field from electric move from high potential to low potential, and test charge all paths these follow that path. Okay, now calculate the potential difference here, final potential minus initial potential, that's the work done. Sorry, potential equal to work done by test charge actually. So that is equal to means electric field from I to F. I to F, that is minus sign E dot ds. Minus sign came from charge a higher potential to lower potential, so that is low value, this high value, from like suppose my my 3 minus 10, that is a minus 7. That's a mathematically okay. That's a algebraically, that's a minus E dot ds. And E ds both are in same direction, so we get minus I to F E ds cos theta. So cos 0 degree, and cos 0 be the 1. So I to F E ds. Okay. Now E outside the integration, I to F ds, and integration of ds is s, limit I to f, and suppose that I to f integration says that the that is that position of initial minus position of final. Yes, final minus s initial. So actually that is a ed. So S final, S initial in position of S here, that is S final minus S initial, that is a S initial and S final. If I minus these two, that is scalar quantity, obviously that's a D. Okay, that's a D, E dot D. Okay, now same case, and the test charge move in another path. Suppose test charge moves, suppose I to here, then I to suppose I to C, and then move C to F, and this pink color path test charge move. And if test charge move pink color path, so potential difference of V F minus Vi, if choose another path, that is V F to Vi, Vf to minus Vi, so we get 2 point potential here, I to C and C to F. Actually C to I or means potential of C to I plus potential of F to C. So here we see that is now calculate potential here. If test charge move this part, pink color part, okay. So you see that if when test charge moves C to I or I to C, actually I to C, that's the test charge moving same surface, same equipotential surface. So if the same equipotential surface, suppose Vc minus Vi, the both value be the same. So that's why they cancel. Potential of Vc that is equal to Vi. And now if I see the DC to F, and if I calculate the potential C to F, means for F to C, and potential C that is also equal to potential I. So we get the same value. So potential F minus potential I. So we get that the Vf minus Vi. So that is equal to, know that is E times D here. Okay. So see that very carefully. Actually test charge moving, that is independent of path. Okay. That is the independent of path. The path independent actually. When test charge moving, if I calculate potential, that is a path independent. Okay. That's physically prove that. If I calculate mathematically, they also get the same result also. Okay. So another method number 2, same condition, Vf minus Vi. So C2I, that is a 0, plus when charge particle move from C to F, so potential Vf minus Vi, that is a cos 0. So that is equal to, okay, final charge move C to F, C to F, and that is equal to EDS cos theta. So that is minus EDS cos, and suppose consider test charge, suppose here the cos value important here, plus test charge, and at that direction suppose electric field in that direction. I say this angle is 45 degree for easy calculation, actually the 45 degree, and so that the angle is cos 45 degree. Say the assumption these is the angle is 45 degree. Angle is 45 degree. Sorry, this angle not. This angle is 45 degree. This angle is 45 degree. Okay. So this angle also 45 degree. Okay. This is alternate angle. So we get cos 45 degree value. So cos 45 degree, we know that. So cos 40 is actually a 1 by root 2. Okay. So that is C2F. That is a E minus cos 45 degree dot ds. If I choose any value, if I are confusing the 45 degree, if you choose any value of like that, suppose if you choose a theta, this angle is theta. Suppose this angle not 45, this angle choose a theta, you get the same result obviously. Okay, choose the unknown value of theta. So minus E cos theta C2F, that is ds. So integration of ds is the s. So minus E cos theta, and the length is C2F is the s of f minus s of c. So actually in that oriented of, but we need that. So that is the component part. We need a component. That component is the s is the same component. The angle is theta. That is a hypotenuse. That is a base. Suppose base is the s. Okay, and the hypotenuse is unknown x. So base by hypotenuse, that is equal to cos theta. So x equal to a s x equal to s by cos theta, or d by cos theta, both are the same. Okay, or called d by cos theta. These are s actually the displacement, but s is, if I indicate that s turn into d, that's s turn into d. So that is d by cos theta. So cancel these two, that is you get e minus d. In mathematically, if you choose any value of theta, not only 45 degree, any value of theta, we get a result is E minus D, the potential. Okay. So that is the say that that is actually that is the potential is a path independent. If you calculate potential from, move a test set from, if calculate equipotential surface to another surface, if I choose from straight line or choose any bending path, we get actually the potential value be the same, means a path independent, which is any value of theta. The mathematically that's also the true, and in, behind the physics also that Vf minus Vi both are the same, minus E minus D times D. So write a notes or key point is that the same as result on previous topic, the potential difference between two pointers. So potential difference between two pointers does not depend on the path. Doesn't depend on the path connecting to them. Connecting to them. Actually independent of path. That's a part one. And 2 points, number two, the main important, the moral, actually number two is the moral of the story actually means when you want to find, when you want to find, okay, the potential difference between 2 points, find potential difference between 2 points. By moving a test charge by moving a test charge between the between them between them the electron move from lower potential to higher potential, between them an electron move from, means very important, lower potential to higher potential, and the proton opposite of electron, that is move from higher potential to lower potential. When the electron move from, suppose take a concept, take an example for understanding this potential concept. Actually they are the independent of path, okay, between the 2 points moving from test charge between them, that's the independent of path. Independent of path. Independent of path. Okay. Now take an example here. Suppose here the at point, suppose the point is A and potential at point is VA. Suppose there is test charge and the potential, suppose any value, suppose consider the 100 volt potential. Okay. 100 volt potential here. 100 volt potential, and choose another point B. The potential at point B is a VB. Suppose that is a 10 volt potential. That is a higher potential, that is a lower potential. Now move a test charge from this path. Actually choose this path and here. This path. And call this line obviously. That line is a L, and choose a very small amount of length is DL. And then vectorically in that direction DL, and that short path is now okay, this, and choose an arbitrary electric field in that direction. Obviously suppose that is a arbitrary electric field. Okay, if you want to move a test charge from higher potential to lower potential, the positive potential, okay, suppose plus Q means a proton, positive charge. Positive charge proton move higher potential to lower potential, and electron negative charge moves the lower potential to higher potential. So potential at VA, that is, we know that actually that is a minus, okay, obviously that from A to infinite, from point A to infinite, that is E dot dr, E dot dr. So there is a minus from infinite to point A. If I potential is infinite to point A, but that is a minus is ignored, that is a limit to shift. Otherwise, that is a, if you confuse that, that is infinite to point A, it is E dot E dot dr. Okay, and the potential at point B, that is also the B to infinite E dot dr. So minus infinite to B, same E dot dr actually mean, so I minus change, that's the limit will shift. Okay, so potential difference between these two B's, that is a VA minus VB, that's the potential difference, that is equal to A to B E dot dr. There's a potential difference, that's very important concept. What is the potential difference between? If you want to change the limit, obviously that's get a VB minus VA, that is equal to from get minus A to B E dot dr. Okay. Now here dr is the length, actually the path length, so we get a dl vector. So that is equal to minus A to B E dot dl. vector. Now bring a charge from home to a place at B. So what is the work done? Okay. So what is the concept being work done? Bring a test charge from move here, point here to that. Okay. First we need a work done. For bring test charge infinite to point A. Infinite, suppose bring a test charge from home, from your drawer or desktop PCs, and just pluck the 1 coulomb positive charge and place that BA or A point. Okay. Suppose you say that bring a positive charge, positive 1 coulomb charge, uh, move from home to point A. That is obviously equal to work done by me or by you. Both are same. Work done me by you. That is Q test charge, the potential at point A, VA, that is times Joule. Same concept. Bring a positive test charge from home to point B, W by U, that is Q times VB times Joule. Okay, so the potential difference is that the potential difference is Q, or work done maybe actually change. There is some Q VA minus VB, that is change in work done actually, that is a delta W or some W, that is equal to change in kinetic energy of B minus kinetic energy of A. We know that. That is a what kinetic energy theorem? That is what KE theorem. Okay. We know that from class 11 physics actually. So what kinetic energy theorem? So if a charged particle move here to that point, if charge move, so there is some velocity actually. If there is a velocity, there is a kinetic energy. If also a potential energy, there is obviously a kinetic energy. Okay, the energy is conserved. Energy neither carried nor this energy is conserved. So that's a energy place. Okay, so kinetic energy, potential energy, both energy are present in that situation. Suppose another top example. If I put suppose a, a mug, coffee mug, and this coffee mug contain 100 volt potential, and bring that charge from this coffee mug to potential to is a very small teacup, cup of teacup, and there's a very small, that 10 volt. Okay, so here from Gauss's law, from charge from big bucket to the small bucket to place, so need some work done actually, very important. And there's a Gauss's law, and this charge is enclosed here. Okay, these are tester is enclosed here, this tester obviously enclosed here. From Gauss's law we know that from here, first copy the diagram. Okay, so from Gauss's law you know that closed integral E dot area, suppose dA vector, that is equal to charge enclosed. This charge is enclosed by that surface, that is enclosed integral over epsilon naught, permittivity of free space. Okay, so potential at a point P or any arbitrary point, that is a potential, suppose that any arbitrary point P, that is equal to P to infinity, that is E dot dl, that's the length dl, and the potential difference VA minus VB, that is equal to basically A to B, that is E dot dl. Okay, so if I consider the same surface, if I both surface be the same, means the equipotential surface. So if that is equipotential surface, potential surface, so VA equal to VB. If VA equal to VB, so obviously that E dot dl be the 0, because the gap is VA minus VB, that value will be the 0. That value will be the 0. So clear, the net work done actually check if I from test charge move here to that point. Okay. Okay. So if I say equipotential, that is a 0. That's the concept. Okay. The charge move from one surface to another equipotential surface. There's a path independent actually. Okay. There's independent of path. Just only suppose if that is R, this person vector actually is R, shortest path. Okay. If I say that short path R, so they just not depend on that path. They are your shortest path actually. Okay. That's so easily to calculate. Okay, so today end the class here. If any doubt, put in comment section. I will try to give the answer. Next class we discuss potential due to a continuous charge distribution, line charge, or calculate potential on a plastic disc. Okay, these two are the very important. Okay, so today end the class here. Thank you.